let us look at intersection and union of subgroups. Let's look at it using an example. So we have this group. Remember, we did a 12-hour clock. So this is that group. In general, we call it as Z12 group, integer addition modulo 12 group. And this is the Kelly table for this. Now the subgroups of H are this. Now how did I get these groups? Take each of the elements of the group 0, 1, 2, 3 to 11 and generate it. So take 0, 0, 1, 0, 0, 2, 0, 0, 3, 0. So you keep getting zeros. So you get the subgroup which contains only 0. Now you take 6, 6 times 0, 0, 6 times 1, 6, 6 times 2, 12, which is 0. 6, 3 is 18, which is 6 again. So 0 and 6 is the subgroup. Similarly, we take or treat each of these elements of the group and use it as a generator. Okay. Now this, this set of subgroups that we have, we can represent it in a lattice diagram. So let's do that. So here you have the entire group. This is T, S, R, Q, P, and O. These are the various subgroups. Now remember, multiple generators may generate the same subgroup. So we are combining them into the lowest generator. So if 4 and 8 generates the same subgroup, we show it as 4. Here, remember, this T is the entire group itself. So here, T is equal to H, which is a trivial subgroup. And this is the subgroup containing only the identity. So again, this is the trivial subgroup. Right? So these are the trivial subgroups, and these are the proper subgroups of the group H or Z12. Now let's look at the intersection of these subgroups. Now let's look at the intersection between S and R. So S intersection R gives us what? 0 and 6 only. So 0, 6 is a subgroup of order 2. R intersection Q will contain what? It will contain 0. That's all. So this is a trivial subgroup containing only the identity. Now S intersection Q gives us 0, 4, 8, which is again a subgroup because Q is a subgroup. So S intersection Q is equal to Q, which in any case is a subgroup. So intersection of subgroups of a group G in general is always a subgroup of G, since subgroups always have the identity E in common with the group, which means at the least the intersection will contain the identity. And a subgroup containing only the identity is a subgroup. If a subgroup is contained in another subgroup, then the intersection between them is always a subgroup. So here, this and this is a subgroup which is entirely contained in S. Then their intersection naturally will be a subgroup. So that was the intersection of subgroups. Now let's look at the union of subgroups. S union R. So S union R will give us 0, 2, 3, 4, 6, 8, 9, 10. So this is not a group. How can we say that? Let's take 9 plus 10 is 19, but modulo 12 is what? 7. 7 is not there in this group. You just add any two numbers and see whether it is there in this group or not. The first occasion where you get a situation where it is not there, we can say it is not closed under the group operation and hence not a subgroup. R union Q is 0, 3, 4, 6, 8, 9. So again, it's not a subgroup. S union Q, S union Q. Now, in this case, this is contained in this. So, which means their union is S, and S is a subgroup of H. So, that means S union Q is subgroup. Now, let's look at this. S union P is a subgroup because this is part of this 0 and 6. R union P, 0 and 6. Again, P is there as part of R. Q union P. Now you notice that you have 6 here, but it is not there here. So it is not a subgroup. Otherwise, also you can just take 2 by 2 elements and keep adding them, modulo 12, and see whether they belong to the union. So the union of two subgroups is a subgroup if and only if one of the subgroup is contained in the other subgroup. So in general, we can say if H, K are subgroups of G, then H union K is a subgroup of G if and only if H is a subset of K or K is a subset of H. So that was intersection and union of subgroups. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.